Okay, it's 10:01 on my clock, and that will declare that the starting time. Okay, so hello everyone, and welcome to the LINCC Tech Talks. So we plan to deliver these in this forum in Zoom virtually every second Thursday of the month at 10 a.m. Pacific times. And you know, the goal of these talks, as we described in the community post and on online and in this mailing list, is to showcase work done by broad Ruby software and archives community, and all of these efforts which are designed to enable LSST science. And we hope that these talks will provide a useful forum for a range of groups and interests and authors to present and learn about and discuss efforts of interest in analysis of LSST data. So today, this will be an inaugural talk, so we'll just start with the LINCC effort. And so this will be given by Jeremy Kubica, who is Director of Engineering for LINCC project. So he first encountered astrophysics while doing his PhD in robotics at Carnegie Mellon University. And then he worked for more than 50 years on large-scale machine learning and software engineering problems at Google before joining us here at LINCC. And his interests, in addition to machine learning, are scalable data structures, algorithms, data structures. And he's authored a number of introductory computer science books, my favorite title being Data Structures the Fun Way, which I guess I have to read to learn how to do that the fun way. And then, so Jeremy, take it away. We will be monitoring for questions in the chat and the Slack channel. And I think we will do them at the end of the talk, and especially then in the end, use the raise hand feature to ask questions. Okay, Jeremy.
Excellent. Well, that sounds great. There's going to be a lot of time for discussion at the end. I want to try to reserve almost half an hour. We're probably not going to do that, but as close as possible for open discussion, for feedback from the community, for any questions we have. But feel free to jump in with questions in the middle anyway, at the same time. Today, I'm going to be talking about the LINCC Frameworks team, the mission, the current set of projects we're working on, and how members of the broader community can collaborate with us and work with us going forward. All right, so the first question is, what is the LINCC Frameworks team? So LINCC is one of those great acronyms that actually embeds another acronym in it. It stands for the LSST Interdisciplinary Network for Collaboration and Computing. And I don't know how many people on the actual LINCC Frameworks team know that acronym off the top of their head, but that's what it stands for. The Frameworks team is a collaboration between multiple institutions, including University of Washington, Carnegie Mellon, LSSTC, University of Pittsburgh, and Noir Lab to build software frameworks and systems for key LSST science. And so I'll explain what that means in the next slide. The PIs for the project are Andy Connolly at the University of Washington, Rachel Mandelbaum at Carnegie Mellon, and I'm Jeremy at Carnegie Mellon. I oversee the engineering at both locations. So for those of you who have seen earlier versions of the presentation, this is what I consider the most exciting update slide that we have since the PCW in August. Our team is growing. A lot of members of the team were due to start or had just recently started at when we presented at the PCW in August. Now we have a whole bunch of people started working on projects and ramping up. The team consists of approximately, or will consist of approximately 15 people split half and half between Seattle and Pittsburgh, with about 5 software engineers and 3 project scientists at each location. So you can see we've got most of the software engineering team in place at this time and a significant number of the project scientists. There's a link at the bottom of the page if you want to find out more about the team members. There's a little bit of biographies for each team member. So the framework's mission is to enable scientists to develop scalable and productionized software and algorithms in collaboration with the broader community. So this is a lot of information packed into a single sentence. So let me dig into a few of these aspects and talk a little bit more about what they mean and what they mean for the community. So The first point is that the team primarily, its mission is engineering and algorithmically focused. We want to develop software that enables the scientists to do science. The second thing is we want to do this in a collaborative way. We want to collaborate with other software efforts. It is not an explicit goal of the team to write all new software packages from scratch. In fact, completely valid projects may include contributions to existing code bases or joining existing projects and helping to provide expertise where it would be useful. We're looking to leverage existing tools, specifically the Rubin Science Platform. We want to build on top of all of the great work that's been done there and make sure that everything we do works seamlessly with what has already been provided by the Rubin Science Platform. And in addition, standard community tools and libraries, such as everything from individual packages to large collections like AstroPy or SciPy. We want to coordinate with the community to avoid unnecessary duplication of effort. We know that there's a lot of really good work going on. We want the work that we do to be additive and not duplicate anything unnecessarily. So the LINCC Frameworks team is going to look at multiple different avenues for collaboration and coordination. This tech talk obviously is the first one where we're looking to broadcast information out to the wider community. We're going to utilize things like the Rubin community forums to publish information. But in addition, we're going to have several more formal venues that we use for collaboration, such as workshops where we bring together members of the science community to get feedback and present the work that we're doing. We actually had one of these in March that I'll talk about a little bit later. Anybody who is at the PCW has seen an overview, but I want to talk about how that's inspired the first round of projects that we're working on and how we're going to use workshops in the future to help kind of refine the mission. Hack weeks are ways of providing tutorials, demos, hands-on training for the new tools and frameworks developed and make sure we get those out to the community. And then incubators, I'll go into a lot of detail in the next slide. I think this is one of the most exciting aspects of the project. It's going to provide an opportunity for scientists to work directly with the team to get their science applications working. And in addition, LINCC Framework members have joined science collaborations and are working through the science collaborations to help those collaborations to further projects that are already ongoing. So there's a whole bunch of different venues we'll have to work with the broader community. So I'm going to deep dive a little bit into incubators because I think this is probably going to be one of the things that is most exciting and interesting to a lot of the people on this call. Incubators will provide support for the researchers at LSST member institutions and the broader science community to work directly with our team, the frameworks team, to apply or possibly even develop new tools for real-world research problems. And the goal here is really to establish a beneficial collaboration that helps both these research teams get their research done and the LINCC Frameworks team to develop better software. So what does this process look like? It is starting in early 2023, and there'll be a lot more information coming out through some of the communication channels I mentioned as this process goes on. But roughly, it's going to be an open proposal process managed by LSSTC, where researchers can submit proposals. About 6 projects will be selected each year, and at least 3 of those slots will be awarded to teams led by researchers at LSSTC member institutions. The goal is then to kick off a 3 or possibly even longer month collaboration directly between the research institution and the and the frameworks team. To support this, some amount of funding, around $20,000, will be provided to offset travel costs, provide graduate student salaries, pay summer salaries for faculties, etc. So what could these incubators look like? So here's one example implementation that I think would be a very positive experience. A research group has a new research idea that maybe has a unique computational challenge or requires using new computational tools that the frameworks team is developing, or possibly even new tools overall. Maybe they have a problem that needs to be scaled up by a factor of 10 in order to handle the data coming from Rubin. They write a proposal, submit it to the process. LSST selects their proposal, and it gets funded. Then the engineering team, the LINCC Frameworks team, and the research teams collaborate on the joint research project as proposed. And one way this could happen is something like a graduate student spends 3 months at one of the with one of the LINCC Frameworks teams, maybe in Seattle or in Pittsburgh, in person, collaborating directly. Maybe, depending on how this is set up, it's a virtual collaboration, but there's a tight collaboration on this work. And we expect a lot of very positive outcomes to come out of this for both groups. First and probably foremost is we hope that a lot of this work will result in joint scientific papers where the grad student is the first author and can really push their research to the next step. New computational tools get created or maybe refined as they're applied to real problems, and we see how they actually function in the world. And then those tools can then be propagated to the full Rubin community to help enable further science. The research team PI might get pilot results from the early work that can then help their research by going into their next NSF proposal. Knowledge is shared between the two groups, in particular, how to use the software or where the software starts to break down and how it can be improved by actually using the software and seeing hands-on what happens. And a foundation is created for future collaborations. As one of the running themes throughout this entire talk, we're really interested in collaborating, and we hope to build really strong foundations. So that was a deep dive into one of the future, here's how collaborations could go, and here's how it could operate in the future. Given that, I'm going to now take a step back and look at where we've been and what we're doing at the moment to set kind of the stage of what the current scope of work is. So I'm going to start off with the workshop from March of 2022 called From Data to Software to Science, which really was looking at trying to get the community together to learn about what are the scientific use cases for early LSST data, what are the technical challenges that come up, what is common among both those science use cases and technical challenges that then we can look at trying to solve broad problems, and what technologies either currently exist or are being developed or need to be developed in order to address these challenges. And at the same time, promote the development of a broad and inclusive community of researchers engaged with LINCC frameworks. Again, this goes back to having a collaborative, open community. The workshop resulted in a paper. It's a nice light read. It's a little over 250 pages, but it has comprehensive information about the science use cases and the technical challenge, and is really interested in sort of seeing the scope of items discussed. So the science use cases fell into about 7 research areas. Now, these weren't one-to-one mappings with the LSST collaborations, but rather were examples collected from the community that were then clustered into a bunch of similar research areas. And we ended up with about 50 research use cases. And again, those aren't meant to be exhaustive or comprehensive. They're meant to be examples of how we can use Rubin data in the future to drive new science. And they fell into roughly solar system science, local universe static science, local universe variable and transient science, extragalactic static science, extragalactic variable science, extragalactic transient science, and cosmology. And you can see they roughly fell in there. And if you look at the LSST science collaborations, a particular science use case might fall into multiple clusters or be of interest to multiple science collaborations. So as I said, there's not a one-to-one mapping. From those, we then looked at what sort of problems they all have from a computational point of view and from a cross-cutting, what could help all of these cases. And this is a table that came out of the workshop and appeared in the paper. And on each row is one of the clusters of scientific use cases. And in each column is one of the cross-cutting technological problems. The main point of this is to show that, yeah, a lot of these problems apply to a whole bunch of science use cases, and they're not unique to a single scientific study or even a single science collaboration. It's tools that are needed across the entire Rubin community. And so we're hoping to look at and engage in a lot of these cases where we can help out a lot of different science use cases by providing foundational technology to support all of them. So the 7 areas were identified as the technical areas. For some reason, 7 turned out to be the magic number for all the clusters we generated. And roughly those corresponded to the ones I'll go through. Several of these are ones we're working on at the moment, so we'll actually go into the next level of detail about things we're looking at now and collaborations we have ongoing. I'll just do a very quick run through of, okay, here's the common themes that we saw in terms of technical challenges. So the first one is scalable cross-matching. This is the spatial join problem. We have a whole bunch of observations coming off of Rubin, and they have sources, and how do we find the corresponding sources in other catalogs or similar sources for the statistical analysis. And the data sizes are what make this problem really exciting. Photometric redshifts, there's a lot of really good work already going on for software for photometric redshifts, but there's also still upcoming challenges that we foresee in terms of supporting even more algorithms or potentially scaling up to higher data sizes that we are looking at helping out with. And we'll go into that one in more detail as well. Selection functions were one that came up. The Rubin Science Platform data management team has a selection function capability and was looking at how do we extend these to broader science use cases? Can we create example use cases that people can then use to model their own selection function development? Scalable job execution system. One thing that came up a lot is, okay, after we get the data, we're going to compute time series or images or models from it. And then we have a lot of time series images or models. How do we then run a large analysis on those? Maybe when we have data sets of billions of sources, time series, and we want to run some sort of distributed processing. Sky image access and reprocessing at scale. The Rubin Science Platform is doing a lot of heavy lifting in terms of producing the data products and images. But a lot of the science use cases also came out and said, well, what if we want to then take this and reprocess it with a different algorithm or a different set of filters or parameters? How can we do that at scale for our particular science use case? And the same type of thing came up for image access and analysis at scale. Questions such as, what if we need different types of cutouts, or what if we need to take object level images and apply a different deblending or classification algorithm than will be applied during the data management pipeline. And so both of those have questions of how do we do them on sort of an ad hoc basis for different analyses at scale. And then the final one was time series analysis and support infrastructure. Time series arise in pretty much every single scientific cluster at the very least that we looked at. And there's a lot of questions about how to do this scalably, how to support a wide range of algorithms. And there's a lot of good work out here. But one of the questions that came up is, how do we do this in such a way that it isn't 20 groups all trying to reinvent their own approach for doing time series? How do we do this in a way that benefits the entire community? All right, so that gave us the starting point of these projects or the starting point from which to work with. And as we started to ramp up the team, the way we did it is we started with a short series of starter projects to really learn about the space, to learn about the code bases that exist, to learn about the problems, and help transition to focusing on longer term contributions. So we picked roughly 5 of these, and we'll talk about 4 of them today. I'm going to hand them off to various people, which are cross-matching, time series, PhotoZ, moving objects, and basic infrastructure for the team. And we'll talk about the first 4 in there. But one thing I want to call out is that 3 of these are being done in collaboration with existing projects. So the PhotoZ work is being done in collaboration with Desk, and actually with members of the team who have joined Desk and are contributing to Rail and QP. Similarly, the early time series work focused on getting some additional libraries and functionality into AstroPy, so it would be available to the wider community. And then moving objects is working with the KB mod software package. So this just goes to reiterate that there's a wide variety of ways that our team can work with and support the wider science community, some of which will involve building entirely new software, and some of which will involve lending our expertise and helping out on projects where we think we can provide support. Before we jump into the projects, I want to quickly talk about the frameworks developmental approach. This is similar to LSST and the Rubin Science Platform in that we're trying to bring in industry best practices and apply them to all the projects we're leading. So this means things like product requirements from gathering product requirements from the users, which are a lot of the people on this call. And we really want to know, what do you need from these products? How do you need them to work? Doing design documents and design reviews, sharing them with the broader community or getting feedback on them. Code reviews for all changes, so that way we know the code we're submitting meets kind of the style guides and also the accuracy that we're looking for. Productionization, testing, coding best practices. In fact, we are using the LSST DM style guide directly to help inform how we are developing our software. And of course, all software is being designed to be interoperable with the Rubin Science Platform and major science packages. We want the software to be additive to the great work that's already being done. Now, this is the process we're using for the projects where we are leading the development or driving most of the development. For some of the projects where we're joining something that's already in place, we are, of course, going to use the established processes and styles for those existing projects. For projects that have been around, they've already got techniques that are working for them. Our goal is not to come in and change things, but rather to contribute. So this is mostly how we are looking at projects where we are doing the majority of the development. All new software that we develop is going to be open source and available to the community. All right, with that, we're going to do a very quick lightning talk series about 4 of the projects that we started as starter projects and we're now looking at for more longer term development. So we're going to start with Sam talking about cross-matching.
Hi, just want to make sure everyone can hear me.
Yes.
Okay. All right, cool. So I'm excited to go into a light dive of the work that we've done with the cross-matching so far, the LINCC team. As you saw a couple of slides ago, cross-matching was pretty much double check marked for every science case. So it's a necessary evil to nail this down and get it right. And so, yeah, we're looking for the expectations of LSST doing kind of spatial joins of around 10 billion objects to potentially 1 billion objects in catalogs. And we want to make this extremely user-friendly, but the way we're doing it right now is it's built on how we're indexing the catalogs that we're ingesting based on an extension of the IVOA format for HIPS. And we're calling this HIPS-cat for HIPS catalog, where we essentially take the sources and partition it in a balanced spatial way through different orders of HIPS maps. We're doing this so that it will enable fast parallelization and optimization for these joins, along with post-processing, because this framework is designed to enable these distributed computations and cross-matching through these catalogs. And the goal is to enable the scientists to rely on the results that they want from these cross-matches. So we're doing as much as we can to enable that as much as possible. And also it just focuses on maintainability and productionization. So if you're interested, you can reach out to me, or we have a Slack channel for cross-matching. You can go and pass it on, Jeremy.
Yep. All right, move to Nevin, who will talk a little bit about the time series work we're currently looking at.
Right, thank you, Jeremy. Yeah, so what I am trying to work on, leading the effort on developing the framework for analysis of time series. And for instance, Drew, in the next slide, will talk about Rail, which is a framework for photoz's. We are trying to replicate something similar in the time series world, so where you can have one-stop shop where you can start your time series analysis. What I'm really looking for and what I really like is the light curve package that some of you might be familiar with, which is a package for analysis of Kepler and test light curves. which is very well accepted in the community. And how did that happen is because it lowered the barrier to entry significantly. By the end of this talk, you can go there and you can play with Kepler and test data and do scientific analysis. And I think what we are trying to do is something very similar, where you will be able to quickly and conveniently access time series data and then wrap around various time series tools that already exist or need to be developed. Our initial project that we are developing now for the next couple of months will focus only on a couple of scientific cases while we are ramping up. One of these will be period finding in general, periodograms, RLR stars, as maybe that we are better focused. And Jeremy already mentioned one of the contributions that Doug did, who's in this talk, is, for instance, he added the multi-band Lomskargel periodogram in AstroPy. And of course, this is something that will be very useful for LCST with multiple bands. The other effort will be AGN science, structure function calculation, all of these various AGN stochastic modeling algorithms. We believe that these two science cases in the next couple of months will give us a good handle on all the different problems that one could expect in time domain. And then, of course, we are looking forward to branching out further. Okay. So that's from me, Jeremy.
Yep. All right. And now, Drew, we'll talk about PhotoZ.
Hello, everyone. I'm Drew Oldag. I'm a software engineer on the LINCC Frameworks team at the University of Washington. Currently, I'm working on Rail. Rail is the Redshift assessment infrastructure layer. It was started by the Dark Energy Science Collaboration, but we're really interested in it not being used by just that group, by a much larger group in general. If you're not already familiar with Rail, it's an open source Python-based tool to help evaluate the performance of Redshift estimation models and a really well-defined, reproducible apples to apples kind of comparison. To do these sorts of comparisons in a reproducible way, it operates in 3 distinct stages. There's a creation stage at the beginning, where a large body of realistic but artificial data is produced from a smaller, well-defined initial data set. There's an estimation stage where multiple Redshift estimate models can be trained, executed, and those results persisted in multiple different formats. And then an evaluation stage where the results of those estimation models can be compared against each other using a multitude of different metrics. Dark Energy Science Collaboration has already included several Redshift estimation models in Rail, as well as a good number of summary and comparison metrics. However, primary goal for LINCC Frameworks and my job here is to expand the usability of Rail beyond Dusk by making it as easy as possible to incorporate new metrics and new models. And the beauty of Rail as it stands right now is that it's meant to be flexible, it's meant to be very extensible. And the belief is that as more people contribute to it, the suite of metrics and models will increase, and the total number of use cases will grow beyond just the initial thought. And for the same reason, we also have a really strong interest in incorporating Rail into the Rubin Science platform, just to make it as easy as possible to get as many people using it and put it in front of as broad an audience as possible. There's a lot more stuff going on with LINCC Frameworks and Rail, but there's only really time to talk about a couple of high points here. But if you're interested in helping out or learning more about it, feel free to reach out to Alex Malls or join the Desk PZ Rail channel and LSSTC Slack workspace. There are lots of folks there who can help you out. Happy to take any questions or get out of the way and let the next person take over. All right, well,
I don't see any questions. We can also return for questions at the end. I have seen at least one question come up in chat. I think it's been answered, but keep going. All right. So the final area we're going to talk about today is moving objects. Early work in moving objects, the starter projects, has been working with the kernel-based moving object detection software package. So this is a software package that has existed for at least 5 years and uses a shift and stack approach to detect faint objects, taking a bunch of images, stacking them together with shifts to account for velocity, and seeing if there's an object we can see in those images, in the combination of images that wouldn't necessarily qualify as a detection in a single image. And as I said, this package has been around for 5 years and has proved valuable for detecting faint objects in earlier surveys. And one of the questions the LINCC Frameworks team is looking at is, how do we then scale this to the volume of data that will be coming off the Rubin telescope? And so these are questions such as improving speed, reducing the computational cost, and reducing the memory usage. At the same time, as with all the projects, we're looking to bring in whatever additional productionization or maintainability that we can. This was one of the first projects we started, so we've actually had some good success here in terms of adding tests, productionizing, accelerating, cleaning up, and adding some new features. Specifically adding lookups for known objects. We know that where the image was taken, we can look in Skybot or the JPL database to actually get what objects were there. And then things like spatial and temporal varying point spread functions. We're aiming for a concrete version 1.0 release in the near future. Again, collaborators, reviewers, or just users are welcome. You can contact me directly at the address there. So that brings us to the end of the prepared material, and we're almost at 30 minutes, which actually worked really well, much better than expected. I want to reinforce a couple points. One is collaborators are welcome for all the projects we mentioned, and even for projects we haven't mentioned that we haven't started yet. If people are interested in collaborating with us, please do reach out. And the second is the question driving us is, what can we do to most help the community? So as you're listening or as you're thinking about this, feedback on what areas we should focus on, what projects we should work on, what software packages could potentially need support or already exists to support the use cases is very welcome and very much needed. So with that, I want to open it up for any questions or discussions we have. And this can be kind of, I don't know, open discussion, or if people want to submit by chat, I can read off those questions. Let me know.
While we are waiting, Jeremy, I can maybe ask,
Yeah.
When you're discussing the projects for incubators, do you have an idea like how will these projects, the proposals, how will they look, how heavy they will be, what will one need to specify, how detailed? Maybe you don't know.
I think Jenno is going to answer that.
All right.
Hi, thanks for asking that question. That's actually still under debate or discussion. And in fact, next week, LSST Corporation has a meeting among the 30 or so member institutions. And one of the topics will be, what should the proposals for these incubators look like? And what should the selection criteria be? So of course, we want input from the software, the engineers, but also that will be an opportunity for the science community to provide input. And I welcome any input that people have. You know, I want them to be kind of short and sweet proposals so people don't have to do a lot of work. But you know, what are the high points they need to hit? But it's still under discussion.
Awesome, thank you. Other questions we might have, or feedback directly, if people want to say, you know, chime in now and say, wow, you're focusing on the wrong things already, you know, feel free. Or you can email me directly. That's fine.
I noticed that there isn't machine learning sort of explicitly called out there. Did that come up as one of the cross-cutting things, or is it just too general to be called out as its own thing?
It was certainly discussed at the workshop in the context of different studies. It generally fell into two categories, if I'm remembering correctly. One is overall support for scalable machine learning and for machine learning packages. And that is something that might actually be an area in the future to consider. There is a lot of really good packages out there already. You know, as I've said, we want to be additive. If there's something good that exists, we want to use that. Second thing that came up was a lot of specific, how do I apply it to this problem? That one is more difficult because each problem comes with its own unique characteristics and unique challenges. So it's hard to say, okay, we're going to have a cross-cutting type of study, you know, that will this type of clustering for this type of object, because it won't be cross-cutting in that case. So I think we will end up, I very much hope so. My background's in machine learning. Personally, I hope we will be doing work to enable machine learning. It's still to be determined what that work will look like, though. Any other questions?
Hi, I was wondering, and maybe you already mentioned it, I missed it. Do you have any like working prototypes going on now? Are they, and how do you feel about them?
So for the projects we're working on, we have a combination of prototypes. So I know there is some prototype on the cross-matching work that we can talk, well, other people can talk about because they're more knowledgeable than I am. For things like the AstroPi contributions, those are going directly into the software.
Right.
For things like KVMod, there's actually a lot of the changes have been pushed to GitHub and are there if the community wants to use them already. So some things are beyond prototype stage where they're actually usable in use. But maybe cross-matching is a good one to talk about a little, because I think that one's more of a prototyping pattern going through. So
Yeah, yeah. There's a link in the slide that I had that it's to the GitHub for what I've done so far. So it's built based largely on my advisor Mario Jurich's LSD, the large survey database, not to be confused. Yeah, the hips cat, all that stuff it's written, and we have a method to partition the catalogs well, and I prototyped it with the Gaia DR3 catalog. The good thing about the partitioning is that it only really needs to be run once for static catalogs. So it is a heavy process for terabytes of data, but once it's run, it runs really well. Right now I have one single benchmark for a cross match, and I've matched the Gaia DR3 catalog with DES Yr1 A1 data, and I think that ran in about 15 minutes. So doing 2 billion sources to, I think, like 300 million sources. I was pretty okay with that. But it has that GitHub repository has like a decent README for installation and the partitioning infrastructure written out. So if anyone wants to play around with it, I'm very open for it.
So to bring that back to the how do we feel about the prototypes, I would say we feel pretty good.
Yeah,
it sounds
good,
like
yeah.
things are going well.
Great, thank you.
Any other questions?
I had a question for you, Jeremy. Is it worth saying something about where people can access the code? I mean, some of it's running on the Link Hub and other places.
Yeah, I mean, so for the code, the majority of that's actually a lot of that is on GitHub, and you can download it, fork it, run it locally. We also have Link Hub, which is a it's basically a service running on the cloud that can allow prototyping or work. Do you want to? I don't know if you want to give a better pitch for it than that. In terms of how the community can use that.
It's a Jupyter Hub interface where we can release some of the applications rather than the actual, just the code itself, so that you can play around and try out some of the techniques. I know KVMod's up and they're running because I know Max does some of the development there. And also it's been used fairly actively, I think, by groups looking at cadence simulations.
Yeah. And it's nice because it has a lot of the packages that you need, a lot of the dependencies all pre-installed. There's some data sets there. It makes starting up a lot easier.
if you were a part of the Housing Science Kickstarter grants, that Jupyter hub that was set up for the Housing Science projects, that's the hub that we're talking about. So it's on lsst.direct.dev.
Jeremy, I could ask another similar question as before. You mentioned hack weeks. What is the time scale that you envisage that happening?
We haven't started planning those yet.
Okay.
I believe they're going to come a little later than the incubators because they're going to be more when there is software to do hands-on. So,
right.
But those will be announced through the various channels when they do come up.
Okay. Any other last minute questions? Okay. Okay, thank you very much, everybody, for attending. So the next meeting will be November 10th, and we'll be talking about, well, time series. What we will be talking about, we invited people from the Light Curve and SunPy projects, which are very successful projects dealing with light series in other contexts. And we hope to learn a lot about their efforts and then think about how we can use that knowledge and experience going forward in the LSST world. And I hope you will join us for that. Wonderful. Okay, see you hopefully next month.